Hello everyone, my name is Alvaro, and in this video we will do the dreaded version of this question right here, which is reverse a linked list, and that is reversing a linked list recursively. Now usually whenever you get asked this question right here, reverse a linked list, if you do it iteratively, the follow-up will be to do it recursively, so I guess you have to be sure of knowing how to do this. So in this video I will cover how to do that conceptually, and then we'll write the code for it. So originally, right, when we were reversing the list iteratively, we were reversing it as we went. So we started here and then we changed the pointers, we went here, we changed the pointers, we went here, we changed the pointers, we went here, we changed the pointers, and we went here. Now, the idea on doing it recursively is that we're going to do it the opposite way. So we're going to go all the way to the end, and then as we go back, then we flip the pointers around, right? So suppose that, for example, we start at 1, we go at 2, without changing pointers, remember that. We go from 1, then 2, then 3, then 4, and then 5, okay? At this point right here, what we want to do is to simply return this as the head, okay? And then we go back in the recursion, and what we want to do is we want to make the next pointer of this 5 right here to point towards this, right? So in this case, so let's repeat again. We will be just using this method right here. So here head is 1, then we call recursively, head is 2, head is 3, head is 4, and head is 5. So at that point, head is 5. Whenever our current node is either a null node or the one after it is null, then all that we need to do is just return this, because this will be the head of the list. And if the node is null, then that means that the list is empty. So we just return an empty list, so that's completely fine. So that will be our base case. So let's write it down. And at that point, right, we go back in the recursion. So when we go back in the recursion, we will have this. So I guess the idea would be to, after checking the base case, we just create the, like, suppose that at any point, right, whenever you're at the current head, you have the reversed list. There you go. So we call it on the next element, okay? So suppose that in here, now you have the reverse list, and this returns the head. So what we want now is we want the element that goes after this. So if head is this, right, then this element right here is head.next. We want the next variable of this node right here to point towards here. So if head is 4 and head.next is 5, then we want head.next, which right now is an arrow that points to nothing, to point towards the 4. So we want head.next to equal the head. Let's try it again. If we're in here, right, in the 3, right, let's suppose that at this point we have the list reversed, right? So this points towards here. We have to do a slight modification, which I'll add in a bit, but suppose that you have like a reverse list here. We have head here is 3, right? So we want 4 to point towards 3. So what do we want to do then? We want to make head.next to point towards the head. This line right here. This line right here takes care of the last element pointing towards ours. Now, what happens once we reach here, right? So what we always want to do, so let's say that we go back all the way to 1, okay? So here we have head.next, which is this 2 right here. So head.next will equal to head, right? And at that point, we will go back to the list, right? But what happens is that we have not gotten rid of this edge right here. So there's a loop on our linked list. Let me repeat. So we reverse. So what we do here is we make 5 points towards the 4, now 4 points towards the 3, 3 points towards the 2, 2 points towards the 1 as we bubble up in the recursion, right? And at this point, head.next. Also, I guess we need to return the reverse list. Okay. So that at this point, what happens is we will have a 2 pointing towards the 1, but we have not gotten rid of the pointer of the 1 that points towards the 2. So our reverse list now will look exactly like this, except that there will be a 1 that points towards the 2. A small modification that we can do is to simply set this head.next equal to none. And this in the end does not matter. Why is that? Let's go again with the recursion. Sorry, I got a message on my phone. So we go here, right? Then we go here. Well, so like here, we go here. We said that the reverse list is reversing this, this, and this. And then here we get to the base case. So here we return the head. And now we are at 4. So at 4, the reverse list is equal to this 5. Okay? The way it is, with the pointer pointing towards nothing. So what we have to do is we have to set head.next equal to the head. So line 15 ensures that 5 points towards the 4. And then simply what we do is we get rid of this arrow right here. So right now we only have one arrow that goes from here to here. Then we bubble up in the recursion again. So the reverse list now looks like a 4 with an arrow pointing from the 5 to the 4. And here we do the same thing. Head.next is equal to head. So there's an arrow from head.next, which is this, pointing towards the head. And then we get rid of this arrow right here. And then we bubble up again in the recursion. So now what we have is the reverse list with the arrows pointing backwards. And then head.next equals head. So we draw an arrow from the 3 to the 2. And then head.next is equal to none. So this arrow right here disappears. We bubble up to the 1. The reverse list now is all this with the arrows backwards. So head.next is equal to the head. So head.next, we draw an arrow, .next to the head. So now there's an arrow from the 2 to the 1. And now we said head.next, so head is 1. We get rid of this arrow. And then we're done. We return the reverse list, and now it would look exactly like this. So if we test now the code, it should work. As you can see, it's a tiny bit slower than the iterative method at times, and that is because recursion can be like maybe slower at times, maybe faster at times. But you can see that the memory usage is definitely smaller. So let's analyze the runtime and the spacetime complexity. So the runtime complexity of this problem is once again big O of n, because we traverse every element in the list at least once. And the spacetime complexity now would be big O of n, because we do n calls recursively, so we go all the way down here. So the recursion stack gets n levels deep. So spacetime complexity, since it's recursion here, and we go all the way down in the recursion throughout the entire list, it's big O of n. So yes, I hope this walkthrough through the recursive solution was a little bit clear, and I hope it helped you understand it. And see you in the next one. Bye-bye.